Welcome back. In Chapter 2, we're going to look under the hood of an Apache Iceberg table. This is where you'll understand the elegant architecture that makes all those features we discussed possible. Think of an iceberg table as a tree with 3 layers. At the top, you have the catalog. In the middle, the metadata layer. And at the bottom, the data layer. Every time you read or write data, you traverse this tree. Let's go through each layer. Starting at the bottom, the data layer. This is where your actual data lives, stored as files on object storage like S3 or ADLS. Iceberg is file format agnostic, meaning it supports Parquet, ORC, and Avro. In practice, majority uses Parquet because its columnar structure is perfect for analytics. But here's something interesting. The data layer also contains delete files. Remember, on object storage, you can't just edit a row in place. So when you delete or update a row, Iceberg has 2 strategies. Positional delete files say, remove row number 234 from this specific file. Equality delete files say, remove any row where order ID equals 1234. Positional deletes are faster to read, but harder to write. Equality deletes are the opposite. We'll explore this trade-off more in later video. Now let's move up to the metadata layer. This is the secret sauce of Iceberg. It's a tree of 3 file types. At the bottom are manifest files, which track subsets of data files and store statistics like min/max values, null counts, and record counts. These stats are generated cheaply at write time, unlike Hive, where separate expensive jobs were needed. Above that are manifest lists, which represent a table snapshot and allow the query engine to skip irrelevant manifest files. At the top are metadata files, which store the schema, partition specs, sort orders, and snapshot history. Every table change creates a new metadata file, giving Iceberg a complete immutable commit history. Finally, at the very top, the catalog. Its job is simple but critical. Store a pointer to the current metadata file for each table and support atomic updates to that pointer. That's it. This simplicity is why so many different systems can serve as Iceberg catalogs, from Hive Metastore to AWS Glue to Nessie to any REST API. Iceberg statistics are superior because they are written at write time, making them fresh and cheap to compute. Min/max values enable file-level pruning. Null and record counts allow for file skipping and accurate row counts without scanning. Quiz time. Question 1. What are the 3 layers of an Iceberg table? The answer: the catalog layer at the top, which stores the current metadata pointer. The metadata layer in the middle, containing metadata files, manifest lists, and manifest files. And the data layer at the bottom, containing data files and delete files. Question 2. What's the difference between positional and equality delete files? Positional deletes identify rows by file path and row number, resulting in fast reads but slower writes. Equality deletes identify rows by column values like a primary key, leading to fast writes but slower reads. Question 3. Why are Iceberg statistics more reliable than Hive's? Because Iceberg writes statistics at write time, as part of the normal write operation. The engine already has the data in memory, so computing min, max, and null counts is nearly free. Hive required separate expensive jobs to gather statistics, which were rarely run, leaving stats stale or missing entirely. That's Chapter 2. Remember this mental model. Catalog points to metadata file, which points to manifest list, which points to manifest files, which point to data files. Every read traverses this tree with pruning at each level. Next up, we'll see this tree in action during actual read and write operations.